Hi all, Larry Feldman again. In this lesson I want to talk about repeated independent events. Repeated independent events are events in which the outcome of one trial has no effect on the outcome of any other trials. For example, if I flip a coin and I flip heads, the next flip has a 50% chance of being heads and a 50% chance of being tails. Just because I flipped heads on the first trial doesn't mean that the second flip will be influenced by the first flip. That's a common fallacy in probability. It's called the gambler's fallacy, and a lot of people think that if you flip 10 heads in a row with a fair coin, that you're more likely to flip a head on the 11th because you're on some sort of hot streak with heads. That's one fallacy. The second fallacy is that you're more likely to flip a tails or a tail on the 11th flip because people think that you're overdue. However, in reality, if you're dealing with a fair coin, the probability of flipping heads or tails is still 50% on that 11th flip. Now, let's talk about an example that I wrote on the screen. A basketball player makes 80% of his free throws. What is the probability that he makes exactly 4 out of his next free throws? So let's say that an S means a successful free throw, and an F is a missed or failed free throw. And I want to start analyzing this problem like this. Let's say that the player makes his first 4 and then misses the last. What is the probability of this occurring? Well, these are independent events. In other words, the probability that he flips, or excuse me, that he, I've got coins on the brain here. The probability that he makes his first free throw is 80%, or 0.8. The probability of making his second is 80%. Third, same thing. Fourth, same thing. Now the probability of missing must be 20%. In other words, if he has an 80% chance of being successful, he must have a 20% chance of failing. Now, if we multiply all these values out, we get roughly 0.08192. Is this the final answer? It's actually not, because the scenario that I wrote here, 4 successes and then a failure, is only one possibility. He could also make his first 3, miss the 4th, and then make the last. And in this case, we have 0.8 3 times in a row, then a failure, which is 0.2, and then another success. But notice that the product here is still the same. It's still 0.08192 approximately, because we have 4 successes at 0.8 per success and 1 failure at 0.2. Now, the third possibility is, or could be, that he makes the first 2, misses the third, and then makes the last 2. And you'll see that again, the probability is the same. So what this problem boils down to is figuring out how many different ways can we arrange 4 S's and 1 F, and then multiplying the number of possibilities for arranging those letters times 0.08192. So let me take a step back for a second. If we look at the letters in the word dog, D-O-G, and we needed to find out how many different ways we could arrange those letters. We noticed that we have three distinct letters, D, O, and G, and the answer is 3 factorial, which is 3 times 2 times 1, which is 6. In other words, we have D-O-G, D-G-O, O-D-G, O-G-D, and G-D-O, G-O-D. So there are 6 ways that we could arrange the letters in the word dog. But what if I have a word like dad, D-A-D? Well, there are still 3 letters, so we want to start with 3 factorial. However, the letter D is repeated twice, so we have to divide by 2 factorial. And we get 3 times 2 times 1 over 2 times 1. Those cancel, and we get 3. Let's look at those. We have DAD, ADD, and DDA. That's all we have. So with this knowledge, let's go back to the basketball problem. We have 4 S's and 1 failure, 1 F. So we have something like this, SS, SS, F. And we want to figure out how many ways we can arrange this combination of letters. Well, it's no different than dealing with a real word. We have 5 factorial, because that's how many trials or letters we're dealing with. And then we have 4 S's and 1 F. So we have to divide by 4 factorial. And this 1F is really a 1 factorial, which is 1. So we don't really have to do, anything with that. 1 factorial is 1. So we have 5 times 4 times 3 times 2 times 1. That was horrible. Divided by 4 times 3 times 2 times 1. And as I said, the 1 factorial is simply 1. These cancel with these. We're left with 5 over 1, which is 5. So let's list these out. Let's say that's the first one. The second one could be this. The third one might be this. Fourth. And the fifth. And each one of those cases has a probability of 0.08192. So to figure out the probability posed at the beginning of this lesson, what is the probability that the player makes exactly 4 free throws out of his next 5? Is 5 times this probability, 0.08192. In other words, the probability of case 1 was 0.08192. Same probability for 2, 3, 4, and 5. They're all identical. So we multiply 5 times 0.08192, and we get approximately 0.4096, which is roughly 40.96%. Now let's generalize this entire result. So let's clear the slate and look at this mathematically for any type of independent event problem. Okay, so in the basketball problem, we looked at a case where we had n trials, and in that case there were 5 trials, or 5 free throws. And we wanted to find the probability of k successes. And in that example, we were using 4, which means 1 failure. And so let's go look at this for a second. Even though I said I wanted to generalize this, I just want to take a step back. If little p is the probability of success, this case has a probability of p to the 4th times 1 minus p, right? 1 minus p is the probability of failure, raised to the 1st power. So using n and k, we have p to the k, because there were 4 successes, times 1 minus p. And what goes up here? Well, if there were n free throws and k successes, there must be n minus k failures. Okay, this is huge, right here. This is for any one case, okay? Now, remember, with the basketball problem, we figured out that there were 5 different ways that the basketball player could make 4 free throws out of 5 attempts. So what we did there is we looked at this 1, 2, 3, 4, 5, and we said there were 5 attempts divided by 4 successes and then 1 failure. Well, in general, we can generalize this to be n trials, n factorial, over how many successes were there, k successes, factorial, and how many failures were there. Again, there were n minus k failures, which looks like this. So all we had to do, let me highlight this. This is how many ways that the person could make k successes out of n trials. So all we had to do, or all we have to do at this stage, is multiply these together. And that's exactly what we did when we solved the basketball problem. So, to summarize, the probability of k successes in n trials is n factorial over k factorial times n minus k factorial, p to the k, 1 minus p to the n minus k. It's a kind of a nasty equation when you first look at it, but when you think about how we constructed it, hopefully you won't find it too intimidating. Again, we have probability of success raised to how many successes? 1 minus p is probability of failure raised to the number of failures, all times the number of ways to arrange successes and failures. That's it for now. I will see you next time. Thanks.